So guys, in this video we are going to deal certain important definitions which is going to be useful for a better understanding in the later coming videos. So of course from the previous video we came to know about electrochemical cells. And through the electrochemical cells we also came to know that there is existing two types of an electrochemical cell. So one was a galvanic cell, the cell which was converting your chemical energy into electrical energy through a spontaneous reaction, and the electrolytic cell, the cell which was converting the electrical energy to chemical energy to bring about a non-spontaneous reaction. So basically guys, to your level, we are going to mainly proceed with the galvanic cells in our chapters, but of course, for a 1 marker, they can ask you, what do you mean by an electrolytic cell or what do you mean by a galvanic cell? So to begin with today's video, we are going to study under the topic galvanic cells. Galvanic cell. So basically we know that it is a cell which converts your chemical energy into electrical energy. Simple ಆಗಿ ಹೇಳಬೇಕು ಅಂದ್ರೆ a galvanic cell is a cell which converts your chemical energy into electrical energy through a spontaneous reaction. And the best example for this galvanic cell is our Danielson. So before diving into the depth of this topic, I am again saying you that in this video you will be coming across a various definition and various concepts which will be used again and again later in this chapter. So if you don't pay attention over here, of course I can give you a 100% challenge, you're not going to understand the rest of the topics. Because all the important foundation for this electrochemistry chapter will be dealt in this video itself. Again I am saying, please keep your ears and eyes open. Okay, so basically first of all I would like to say that what are the things we are going to cover in this video. Okay guys, the first and the foremost thing, we are going to see half cells. What do you mean by half cells? Okay, then we are going to see the importance of a salt bridge. Then we are going to see electrode potential. What do you mean by electrode potential? Then we are going to see the cell potential. What do you mean by a cell potential? An important formula would be seen over here. Yes. Then you are going to see what do you mean by standard electrode potential. What do you mean by a standard electrode potential? To which electrode you will be calling it as an anode? To which electrode you will be calling it as a cathode? Yes. What is a representation of a symbolical representation of your galvanic cell? Symbolic representation of your galvanic cell. So these are the topics today I am going to cover in this video. You could only see that there are many major topics which will be dealt, and of course that is the reason I am saying that all these topics whichever I am going to deal in this video, 100% sure they are going to repeat in your later videos also. So at that interval of time I would be just using their names. So as soon as I use their names, you should come to know that what they are. For that is the reason I am making a separate video which will be involving all these terms with a conceptual understanding. Is that clear? Okay guys, to begin with, as I have said, we are going with a galvanic cell, and the better example for a galvanic cell was your Danielson. So of course when I write a Daniel cell, what do I know is I'm taking a container, two containers basically. So in one container I have dipped my zinc electrode in my zinc sulfate solution. And in another tumbler I have taken my copper electrode which has been dipped in a copper sulfate solution. This is copper sulfate solution. Mark my words now, what I am saying, please clearly understand. Externally, the whole cell is interconnected through a copper wire. Yes, externally I am connecting the two electrodes, and the cell two electrodes with a copper wire, and internally both of these are connected through a salt bridge. Both of these are connected through a salt bridge. Of course, we know the electron flow will be from zinc to copper, yes, and the current flow will be from copper to zinc. So this will be your current flow. Why you are having an opposite direction for the current flow and electron? Yes, of course, we have dealt in our later video, and I hope you are remembering it. Okay, so now our concept begins over here. So first and the foremost thing, I would be dealing with my half cell. So of course, when we are seeing this cell, Daniel's cell, as I am mentioning that, here we could see that electrons are flowing from zinc to copper. What I am saying, electrons are flowing from zinc to copper. That means what is happening at this part, when I consider only this part, that is zinc, which is being dipped in a zinc sulfate solution. That means it is passing the electrons, means zinc has to lose electrons. Andre ಏನು ಆಗ್ತಾ ಉಂಟು, whatever the zinc were there, that is if I write it as in a particular way, if I am going to separate it, only this part if I am going to write, so what is happening, whatever the zinc solid was there in the electrode, that is going into the solution as Zn2 plus. What it is going as? Zn2 plus. That means it is losing 2 electrons. So those electrons, what will be happening through the external connected copper wire, it is going to that of your copper. So how can I write the reaction for this part? Yes, that is zinc, which is a solid, which is a solid, that is your zinc electrode. It is losing negative 2 electrons, to give you what? Zn2 plus. Zn2 plus. So this is the way of your writing. In certain books, they have also given you in this way. I will just write it over here. Zn solid, it will be giving you as a Zn2 plus 2 electrons. It is a bit confusing. Okay, you can write in this way also, not an issue. Just what they have done, this minus 2 electrons they have sent over here. But this is a conceptual understanding. Zinc, which is losing 2 electrons. Losing means what? Negative. So there is a reason I have written over here. Zinc losing the 2 electrons, giving you as what? Zn2 plus. Alva. Similarly, these 2 electrons, now it will be flowing to your copper. Yes or no? So here what happens now, this will be having the electrons accommodated over here. So we know what? So now what happens in this solution, that is if I take this as a separately over here, that is my copper sulfate, in which you have been dipped your copper electrode. What happens in this solution, you will be having your Cu2 plus. So whatever the electrons which has been flowing from zinc to copper, now those electrons will be accommodated over here. So those electrons will be occupied or will be taken by your Cu2 plus, which is present in your solution, and it will in turn get what? Converted to your copper. So once it gets converted to copper, what happens? From the aqueous copper, it is getting converted to a solidified copper. So that copper will come and deposit at the copper electrode. That comes and deposit at the copper electrode. So how can I write this reaction now? That is Cu2 plus, which was present in the solution, has acquired 2 electrons, has gained 2 electrons to give you as what? Cu. So this was zinc solid, it is going into the solution, so it is getting converted to aqueous, whereas Cu2 plus, which was in the aqueous, is getting converted to a solid. Alva. Okay, sir, you were saying about the concept of the half cell, but you have given us the reaction. What does it mean? Here lies the concept. What is that, sir? So whenever we consider a cell, a complete cell, you do remember that a cell is divided into 2 parts. Alva, that whole cell will be divided into 2 parts. What is that part? One is an oxidation half cell. What it is called as? One is an oxidation half cell. Alva, one is an oxidation half cell. Another is what? Reduction half cell. Another is what? Reduction half cell. Are you getting my point? So whenever we talk about a complete cell, overall that cell working has been divided into two half cells. One is an oxidation half cell, another is a reduction half cell. Why it is called as an oxidation half cell? Because you could just see that in this oxidation half cell, it is losing two electrons. Oxidation andre with respect to electrons we have read in redox reactions. Just recall those concepts. Oxidation andre loss of electrons. So zinc is losing the electrons. So whatever the reaction we are going to write, that is zinc on losing the two electrons giving us Zn2 plus, this will be called as what? Oxidation half reaction. Oxidation half reaction. So once you have been gaining the electrons, what is that term called as? Reduction. Since in considering the reduction half cell, what you will be getting? Reduction half reaction. Reduction half reaction. Very much important, guys. Again, I am going to say this. What I am saying, whenever we consider a cell, it is divided into two parts. One is an oxidation half cell, another is a reduction half cell. What do you mean by oxidation half cell? The cell in which your oxidation half reaction is taking place, alva. The cell in which your oxidation half reaction is taking place. That is called as what? Oxidation half reaction. Sorry, oxidation half cell. Similarly, in a reduction half cell means what? The cell in which the reduction half reaction is taking place. Alva, that is called as what? Reduction half cell. The combination of both oxidation half cell and reduction half cell gives you the complete cell. Complete cell barbeku andre iveldu half cell irlebeku. Are you getting my point? Very much important over here. Okay. So this part, for example, Zn is giving you as what? Zn2 plus. Similarly, Cu2 plus is giving you as what? Cu. So this part can be also called as what? Redox couple. Redox couple. The same concept which we have dealt with the redox reaction. You can turn out the pages over there and you can understand what do you mean by a redox couple. But in this point of view, you should just remember what do you mean by a half cell. ಒಂದು ಹಾಫ್ ಸೆಲ್ ಅಂತ ಕನ್ಸಿಡರ್ ಮಾಡ್ತಿದೀವಿ ಅಂದ್ರೆ ನಿಮ್ಗೆ ಗೊತ್ತಾಗ್ಬಿಡ್ಬೇಕು ಏನಂತ. ಯಾವತ್ತೇ ನಾವು ಕಂಪ್ಲೀಟ್ ಸೆಲ್ ಅಂತ ಯೋಚನೆ ಮಾಡ್ತೀವಿ, that complete cell will always consist of a two half cells. It will be always consisting of a two half cell. One half cell will be calling it as an oxidation half cell. Another half cell will be calling it as a reduction half cell. Why is it important, sir? If you just see my earlier video for the Daniell cell, I have written one complete cell reaction ಬರ್ದಿದ್ದೆ ಅಲ್ವಾ. A complete cell reaction napka ಇಟ್ಕೊಳ್ಳೋದು ಕಷ್ಟ ಇತ್ತು. ಯಾಕೆ? Because you are by hearting it. But see now, utilizing my oxidation half cell and reduction half cell, how easily I can write that complete redox reaction. So of course ಈಗ ಏನಾಗುತ್ತೆ, this is minus 2 electron, this is plus 2 electron. So they both get cancels ಅಲ್ವಾ. ಇನ್ನು ಉಳಿದಿದ್ದೇನು? Zn solid plus Cu2 plus aqueous gives you what? Zn2 plus aqueous plus Cu solid. Can you see? So whatever the complete cell reaction we write, it is actually the sum of your oxidation half reaction and reduction half reaction. Mark my words, very much important. This concept will be utilized in your competitive exams. ಇಲ್ಲಿ ನಾನು ಯಾಕೆ -2 ಮತ್ತೆ +2 electrons cancel ಮಾಡಿದೆ? Because they were same and they were having the opposite sign. In a certain scenarios ಇಲ್ಲಿ -2 ಇರುತ್ತೆ, ಇಲ್ಲಿ ಬರೀ 1 ಎಲೆಕ್ಟ್ರಾನ್ ಇರುತ್ತೆ. ಅವಾಗ ಏನ್ ಮಾಡಬೇಕು, ನಮ್ಗೆ ಯಾವತ್ತೇ ಆಗ್ಲಿ ನಮ್ಮ ಸೆಲ್ ರಿಯಾಕ್ಷನ್ ನೋಡಿರ್ಬೋದು, ಎಲೆಕ್ಟ್ರಾನ್ ಯಾವತ್ತೂ ಬರೋದಿಲ್ಲ. ಸೊ ಅವಾಗ ಏನ್ ಮಾಡಬೇಕು, ಅದನ್ನ ನಾವು ಈಕ್ವಲ್ ಮಾಡಕ್ಕೆ ಏನ್ ಮಾಡ್ತೀವಿ, ಕಂಪ್ಲೀಟ್ ಆಗಿ ಆ ನಂಬರ್ ಇಂದ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡೋ ಚಾನ್ಸಸ್ ಇರುತ್ತೆ. ಇಟ್ ವಿಲ್ ಬಿ ಡೀಲ್ಡ್ ಇನ್ ಯೋರ್ ನೆಕ್ಸ್ಟ್ ವಿಡಿಯೋಸ್. ಜಸ್ಟ್ ಫಾರ್ ಅ ಹಿಂಟ್ ಐ ಆಮ್ ಗಿವಿಂಗ್. ವೈ ಇಸ್ ಇಟ್ ಇಂಪಾರ್ಟೆಂಟ್? ಅದನ್ನ ನಾವು ಇಲ್ಲಿ ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕು. So whenever you are writing this one complete cell reaction, you remember, first of all, you should come to know that how to write the oxidation half reaction and a reduction half reaction. So they are very much important. Is that clear? I hope so. There is no doubt in it. You have got the concept that what do you mean by a half cell? Whenever we talking about a cell, a complete cell, you do remember it will be always consisting of a two half cell. One will be an oxidation half cell where the electrode is losing the electrons or it is undergoing oxidation, and another is a reduction half cell where the electrode is gaining the electrons. Is that clear? I hope so. There is no doubt in it. So the next concept we are going to move, an important concept which is called as your salt bridge. Salt bridge. So guys, first of all, you have to understand what do you mean by this salt bridge. Okay. So basically, salt bridge andre, it will be like a U-shaped limb. It will be a U-shaped glass tube. U-shaped glass tube. And majorly it will be containing your protein, that is your agar-agar paste. Okay, agar-agar paste irutte. It's actually a protein. And along with that protein, you will be having certain salts. That salt could be your KCl. It could be your potassium nitrate, KNO3. And even it could be your ammonium nitrate. So these. So a salt bridge andre enu, it is a U-shaped glass tube which will be containing, this is pakka, agar-agar paste will be there. Along with that one, you will be having a potassium chloride or a potassium nitrate or ammonium nitrate. Question arises, Alva, sir, why we are using this salt bridge? That is very much important. So before the explanation, first of all, I would like to say what is the role of your salt bridge. Then it would be easy for me to understand. So first and the foremost thing, the importance of the salt bridge is, remember guys, I'm giving you the point. It maintains the electrical neutrality in the solution. It maintains the electrical neutrality. It maintains the electrical neutrality on both sides. On both cells and half cells, on both sides, it will be maintaining what? Electrical neutrality. Then the second point, it prevents the accumulation of charges in the half cell. It prevents the accumulation of charges. Accumulation of charges in the half cells. In the half cells. Then the third most important thing, it avoids liquid junction potential. It avoids liquid junction potential. Of course, it is not mentioned in your textbook, but these are the important role which will be played in your through your salt bridge. Now the concept arises, what is this salt bridge? Basically guys, I will just give it first of all how the salt bridge looks like. Okay, so this is, as I mentioned, it is a U-shaped glass tube. Okay, here it will be having a diaphragm in this way. As I mentioned, so this will be having an agar-agar paste along with a salt that may be your KCl. For example, if I take as a KCl. Why it is used? So first of all, I would like to deal with the first 2 points. It maintains the electrical neutrality on both sides and it prevents the accumulation of charges in the half cell. What does it mean? So for example, if I take the same cell, Daniel cell, and you just assume that, let me write it once again for a better understanding. Okay. Assume that I have not used my salt bridge in this case. So I just used my zinc electrode and my copper electrode, and they have been connected through a copper wire where your zinc rod is dipped in a zinc sulfate and a copper rod dipped in a copper sulfate. So we know that, of course, the circuit is connected, zinc has to dissolve, copper has to deposit. Though there is salt bridge or not, that is a different case. Electrons flow ಆಗೆ ಆಗುತ್ತೆ, ಯಾಕಂದ್ರೆ ಎಕ್ಸ್ಟರ್ನಲ್ ನಾವು ಸರ್ಕ್ಯೂಟ್ ನ ಜಾಯಿನ್ ಮಾಡಿದೀವಿ. ಸೊ ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ, ಜಿಂಕ್ ಇದ್ದಿದ್ದು Zn2+ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತಾನೆ ಇರುತ್ತೆ ಕಂಟಿನ್ಯೂಸ್ ಆಗಿ, ಅಲ್ವಾ? ಸೊ ವಿತ್ ಅ ಸರ್ಟನ್ ಇಂಟರ್ವಲ್ ಆಫ್ ಟೈಮ್ ವಾಟ್ ಹ್ಯಾಪನ್ಸ್, Zn2+ ಇನ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಇಲ್ಲಿ ಹೈ ಆಗ್ತಾ ಹೋಗ್ಬಿಡುತ್ತೆ, ತುಂಬಾನೇ Zn2+ ಬರ್ತಾನೆ ಹೋಗುತ್ತೆ. ಅದೇ ರೀತಿ ಇಲ್ಲೇನಾಗುತ್ತೆ, ಸಿನ್ಸ್ CuSO4 ಅಲ್ವಾ, ಇದು CuSO4, ಸಿನ್ಸ್ Cu2+ ಏನಿರುತ್ತೆ ಅದು ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ತಗೊಂಡ್ ಏನ್ ಮಾಡುತ್ತೆ, Cu2+ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಕಮ್ಮಿ ಆಗ್ತಾ ಬಂದು SO4 ಇನ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಎಸ್ ಆರ್ ನೋ? Zn2+ ಇನ 2 ಎಲೆಕ್ಟ್ರಾನ್ ಏನ್ ಬಂತು ಅದು Cu2+ ಜೊತೆ ಅಟ್ಯಾಚ್ ಆಗಿ ಕಾಪರ್ ಡೆಪಾಸಿಟ್ ಆಗುತ್ತೆ, ನೋ ಪ್ರಾಬ್ಲಮ್. ಬಟ್ ಕಾಪರ್ ಅಯಾನ್ ಕಮ್ಮಿ ಆಗ್ತಾ ಬಂದಂಗ ಇನ್ನೇನು ಅಯಾನ್ ಉಳಿದದೆ ಕಾಪರ್ ಸಲ್ಫೇಟ್ ಅಲ್ಲಿ, SO4 ಸೊ ನನ್ನ ಈ ಪಾರ್ಟ್ ಅಲ್ಲಿ ನೋಡಿದ್ರೆ, ಜಿಂಕ್ ಪಾರ್ಟ್ ಅಲ್ಲಿ ನೋಡಿದ್ರೆ ಪಾಸಿಟಿವ್ ಚಾರ್ಜಸ್ ಇನ ಅಕ್ಯುಮುಲೇಷನ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಬರ್ತಾ ಉಂಟು. ಅದೇ ನನ್ನ ಕಾಪರ್ ಸೈಡ್ ಅಲ್ಲಿ ನೋಡಿದ್ರೆ ನೆಗೆಟಿವ್ ಚಾರ್ಜಸ್ ಇನ ಅಕ್ಯುಮುಲೇಷನ್ ಜಾಸ್ತಿ ಆಗ್ತಾ ಬರ್ತಾ ಉಂಟು. ಸೊ ಈ ತರನೇ ಬಿಟ್ರೆ ಏನಾಗುತ್ತೆ, ಯಾವುದೋ ಒಂದು ಪರ್ಟಿಕ್ಯುಲರ್ ಟೈಮಿಗೆ 2 ಇಕ್ವಿಲಿಬ್ರಿಯಂ ರೀಚ್ ಆಗಿ ರಿಯಾಕ್ಷನ್ ಸ್ಟಾಪ್ ಆಗಿಬಿಡುತ್ತೆ, ಎಲೆಕ್ಟ್ರಿಸಿಟಿ ಉತ್ಪತ್ತಿ ಆಗೋದಿಲ್ಲ. ಆರ್ ಯು ಗೆಟಿಂಗ್ ಮೈ ಪಾಯಿಂಟ್? ದ ರೀಸನ್ ಯು ಆರ್ ಗೆಟಿಂಗ್ ಹಿಯರ್, ಏನಾಗುತ್ತೆ, after a certain interval of time, without the using of the salt bridge, I am just showing you, accumulation of the positive charges and the negative charges take place at the respective part, and which will be maintaining an equilibrium, and the reaction gets stopped. There will be no generation of electricity. Okay sir, we have understood this. What is the role played now by your salt bridge? As I mentioned, your salt bridge will be taken over here in this solution. Alva, in this solution. Agar paste, not an issue, it is not having any charge, but along with that one we have also took a salt. For example, it is your KCl. KCl ಅಂತ ತಗೊಂಡಿದ್ದೀನಿ. ಸೊ ಈಗೇನಾಗುತ್ತೆ, ಈ KCl ಅಲ್ಲಿ ಈ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಇಲ್ಲಿ ಈಗ ಇಲ್ಲೇನಾಗಿದೆ, Zn2+ ಇನ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಏನಾಗಿದೆ, ಜಾಸ್ತಿ ಆಗ್ತಾ ಬಂತ. ಸೊ Zn2+ ಇನ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಕಮ್ಮಿ ಮಾಡಕ್ಕೆ ಈಗ ಏನ್ ಮಾಡುತ್ತೆ, Cl- ಹೋಗುತ್ತೆ. KCl ಇನ Cl- ಏನುಂಟಲ್ಲ ಅದು ಈ ಕಡೆ ಬಂದು Zn2+ ನ ನ್ಯೂಟ್ರಲ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಕಮ್ಮಿ ಮಾಡ್ತಾ ಬರುತ್ತೆ. ಅದೇ ರೀತಿ ಈ ಕಡೆ ಏನಾಗಿದೆ, ಕಾಪರ್ ಕಡೆ SO4 ಇನ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಜಾಸ್ತಿ ಉಂಟು. ಸೊ ಆ ಕಡೆಗೆ ಏನ್ ಬರುತ್ತೆ, ನಿಮ್ಮ K+ ಬರುತ್ತೆ. ಸೊ K+ ಬಂದು ಏನ್ ಮಾಡುತ್ತೆ, ನಿಮ್ಮ ಸಲ್ಫೇಟ್ ಇನ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಕಡಿಮೆ ಮಾಡ್ತಾ ಬರುತ್ತೆ. ಸೊ ದಟ್ ಈಸ್ ದ ರೀಸನ್ ವಿ ಸೇ ದಟ್ ಇಟ್ ಪ್ರಿವೆಂಟ್ಸ್ ದಿ ಅಕ್ಯುಮುಲೇಷನ್ ಆಫ್ ಚಾರ್ಜಸ್ ಇನ್ ದಿ ಹಾಫ್ ಸೆಲ್. ಈಗ ಹಾಕ್ಲಿಲ್ಲ ಅಂದಾಗ ಏನ್ ಮಾಡ್ತು, ದೇರ್ ವಾಸ್ ಅನ್ ಅಕ್ಯುಮುಲೇಷನ್ ಆಫ್ ಪಾಸಿಟಿವ್ ಅಂಡ್ ನೆಗೆಟಿವ್ ಚಾರ್ಜಸ್. ಸೊ ಆಸ್ ಸೂನ್ ಆಸ್ ಯು ಆರ್ ಯೂಸಿಂಗ್ ದಿ ಸಾಲ್ಟ್ ಬ್ರಿಡ್ಜ್, ವಾಟ್ ಇಸ್ ಹ್ಯಾಪನಿಂಗ್, Zn2+, that is a positively charged, is getting neutralized by your chloride ion of your potassium chloride. Similarly, the negative charge of a sulfate is getting neutralized by the positive charge of your potassium. So this is the main role played by your salt bridge. In case if you are not using the salt bridge, what happens? Overall the potential will get dropped to 0. Potential 0 andre artha eno, there is no electron flowing. For the continuous flow of the electron and for the generation of the electricity, we are using this salt bridge. That is the reason we say that it maintains the electrical neutrality on both sides and prevents the accumulation of charges in the half cell. Coming to my third point, that is your liquid junction potential. Of course, I'm not going to deal with it, what you can say, detailed topic about it, because it is a bit confusing for your level. Just an outline I would like to say. ಸೊ ಯಾವತ್ತೇ ಆಗಲಿ ಸಾಲ್ಟ್, ಯಾವತ್ತೇ ನೀವು ಸೆಲ್ ನ ಕನ್ಸಿಡರ್ ಮಾಡಿದಾಗ ಒಂದು ಅಯಾನ್ ಅಥವಾ ಒಂದು ಸೊಲ್ಯೂಷನ್, ಎಲೆಕ್ಟ್ರೋಲೈಟಿಕ್ ಸೊಲ್ಯೂಷನ್ ಗೆ ಒಂದು ಕಾನ್ಸಂಟ್ರೇಷನ್ ಇದೆ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಇದಕ್ಕೆ ಏನೋ A ಕಾನ್ಸಂಟ್ರೇಷನ್ ಉಂಟು, ಈ ಒಂದು ಎಲೆಕ್ಟ್ರೋಲೈಟಿಕ್ ಸೊಲ್ಯೂಷನ್ ಗೆ ಒಂದು B ಕಾನ್ಸಂಟ್ರೇಷನ್ ಉಂಟು ಅಂತ ತಿಳ್ಕೊಳ್ಳೋಣ. ಸೊ ಈ A ಕಾನ್ಸಂಟ್ರೇಷನ್ B ಡಿಫ್ರೆಂಟ್ ಇದ್ದಾಗ ಅಂಡ್ ಯು ಹ್ಯಾವ್ ನಾಟ್ ಯೂಸ್ ದಿ ಸಾಲ್ಟ್ ಬ್ರಿಡ್ಜ್ ಅಂದಾಗ ಏನಾಗುತ್ತೆ, ಕಾನ್ಸಂಟ್ರೇಷನ್ ಡಿಫರೆನ್ಸ್ ಇರೋ ಕಾರಣದಿಂದ ಇಲ್ಲೂ ಒಂದು ಪೊಟೆನ್ಶಿಯಲ್ ಡೆವಲಪ್ ಆಗುತ್ತೆ. ಸೊ ಆ ಪೊಟೆನ್ಶಿಯಲ್ ನ ನಾವೇನಂತ ಹೇಳ್ತೀವಿ, ಲಿಕ್ವಿಡ್ ಜಂಕ್ಷನ್ ಪೊಟೆನ್ಶಿಯಲ್. ಸಿನ್ಸ್ ದ ಪೊಟೆನ್ಶಿಯಲ್ ಹ್ಯಾಸ್ ಬಿನ್ ಡೆವಲಪ್ ಡ್ಯೂ ಟು ಯೋರ್ ಎಲೆಕ್ಟ್ರೋಲಿಟಿಕ್ ಸೊಲ್ಯೂಷನ್ ಅಲ್ವಾ. ಈ ಒಂದು ಎಲೆಕ್ಟ್ರೋಲಿಟಿಕ್ ಸೊಲ್ಯೂಷನ್ ಇನ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಇಲ್ಲಿನ ಎಲೆಕ್ಟ್ರೋಲಿಟಿಕ್ ಸೊಲ್ಯೂಷನ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಡಿಫರೆಂಟ್ ಆಗಿದ್ದ ಕಾರಣದಿಂದ ಒಂದು ಪೊಟೆನ್ಶಿಯಲ್ ಡೆವಲಪ್ ಆಗುತ್ತೆ ಅಲ್ವಾ. ಆ ಪೊಟೆನ್ಶಿಯಲ್ ಏನ್ ಡೆವಲಪ್ ಆಗಿದೆ, ದಟ್ ಈಸ್ ಕಾಲ್ಡ್ as a liquid junction potential. Okay sir, what is the use in case if it is developed, what is the problem in it? There is a problem. What is the problem? Of course, we know that when we were dealing with the Daniel cell, I have said that it is giving you 1.1 volt. Ee 1.1 volt yak bantu? It was the measure of only the electron which was passing from the zinc to copper. Est electron hogta ittu, est electricity barta ante adru mele namge 1.1 volt siktu alva. Iga salt bridge na use madilla anದಾಗ ಏನಾಗುತ್ತೆ, always also there will be a difference in the electrolytic solution. Okay, ಅಲ್ಲೂ ಕೂಡ ಒಂದು ಪೊಟೆನ್ಶಿಯಲ್ ಡೆವಲಪ್ ಆಗುತ್ತೆ. ಸೊ ನನ್ನ ನೆಟ್ ರಿಸಲ್ಟೆಂಟ್ ಪೊಟೆನ್ಶಿಯಲ್ ಏನ್ ಬರುತ್ತಲ್ಲ ಅದು ಏನೋ ಬೇರೆನೆ ಆಗಿರುತ್ತೆ. ಸೇಕ್ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ X ವೋಲ್ಟ್. ಸೊ ನನಗ್ ಬೇಕಿರೋದೇನು, ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಫ್ಲೋ ಆಗಿದ್ದರಿಂದ ಎಷ್ಟು ಬೇಕಿತ್ತು ಅನ್ನೋದೇ ನಂಗೆ ಬೇಕಾಗಿದ್ದು. ಆದ್ರೆ ಅಲ್ಲೇನಾಯ್ತು, ದೇರ್ ವಿಲ್ ಬಿ ಅ ನೆಗೆಟಿವ್ ಪಾರ್ಟ್. 1.1 ವೋಲ್ಟ್ ಗಿಂತ ಕಡಿಮೆ ಬರೋ ಚಾನ್ಸಸ್ ಇರುತ್ತೆ. ಸೊ ಅವಾಗ ಏನಾಗುತ್ತೆ, ಆತರ ಒಂದು ವೋಲ್ಟೇಜ್ ಡ್ರಾಪ್ ಆಗಬಾರ್ದು. ಏನೇ ವೋಲ್ಟೇಜ್ ಸಿಗ್ತಾ ಉಂಟು ಅದು ಬರೀ ಎಲೆಕ್ಟ್ರಾನ್ ಫ್ಲೋ ಇಂದನೇ ಬರಬೇಕು. ಆ ಕಾರಣದಿಂದ ನಾವೇನ್ ಮಾಡ್ತೀವಿ, ಅದನ್ನ ಅವಾಯ್ಡ್ ಮಾಡಕ್ ನೋಡ್ತೀವಿ ಆ ಲಿಕ್ವಿಡ್ ಜಂಕ್ಷನ್ ಪೊಟೆನ್ಶಿಯಲ್. ಸೊ ಅದನ್ನ ಹೆಂಗ್ ಅವಾಯ್ಡ್ ಮಾಡಬಹುದು, ಬೈ ಮೇಂಟೈನಿಂಗ್ ಯೋರ್ ಅಯಾನಿಕ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಇನ್ ಬೋತ್ ದಿ ಹಾಫ್ ಸೆಲ್ಸ್. ಆ ಅಯಾನಿಕ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಹೆಂಗ್ ಬ್ಯಾಲೆನ್ಸ್ ಮಾಡಕ್ ಸಾಧ್ಯ, ಓನ್ಲಿ ಬೈ ಯುಟಿಲೈಸಿಂಗ್ ಯೋರ್ ಸಾಲ್ಟ್ ಬ್ರಿಡ್ಜ್. ಸೊ ದಟ್ ಈಸ್ ದ ರೀಸನ್ ದೀಸ್ ಆರ್ ದಿ 3 important roles which will be placed by your, or which will be played by your salt bridge. Okay, is that clear? I hope so. There is no doubt in your salt bridge concept. Also, I have added a video for your better understanding, which you could be seen later in this video. So the 2 concepts till now you had to get clear. One was, what do you mean by a half cell? how to write a oxidation half reaction and a reduction half reaction, and utilizing that oxidation and reduction half reaction, how to write the complete cell reaction. Then we came across with respect to a salt bridge, which we came to know that it is a U-shaped glass tube which will be having an agar-agar paste. Along with that one, you will be having a potassium chloride or a potassium nitrate or ammonium nitrate. You can just see K plus Cl minus, K plus NO3 minus, NH4 plus NO3 minus. Respective ions will go and neutralize the respective ions in your half cells. Then we also saw what do you mean by liquid junction potential, the potential which is generating whenever there is a difference in the electrolytic concentration. Electrolyte solution in tagonirtira, the difference in the concentration iddaga enagutte, there a potential develops. That potential itself is called as what? Liquid junction potential. ನಮ್ಮ ಒಂದು ರಿಯಾಕ್ಷನ್ ಅಲ್ಲಿ ಆ ಲಿಕ್ವಿಡ್ ಜಂಕ್ಷನ್ ಪೊಟೆನ್ಷಿಯಲ್ ವ್ಯಾಲ್ಯೂ ಬರಬಾರ್ದು. ಆ ಕಾರಣದಿಂದ ಅದನ್ನ ಅವಾಯ್ಡ್ ಮಾಡಕ್ಕೂ ಕೂಡ ನಾವು ಏನ್ ಮಾಡ್ತೀವಿ? ಸಾಲ್ಟ್ ಬ್ರಿಡ್ಜ್ ನ ಯೂಸ್ ಮಾಡ್ತೀವಿ. ಇಸ್ ದಟ್ ಕ್ಲಿಯರ್? Okay. So the next concept we are going to deal, it is called as electrode potential. What it is called as? Electrode potential. Very much important. Okay. Now let us see what do you mean by an electrode potential.
A salt bridge, in electrochemistry, is a laboratory device used to connect the oxidation and reduction half cells of a galvanic cell, a type of electrochemical cell. It maintains electrical neutrality within the internal circuit, preventing the cell from rapidly running its reaction to equilibrium. If no salt bridge were present, the solution in one half cell would accumulate negative charge and the solution in the other half cell would accumulate positive charge as the reaction proceeded, quickly preventing further reaction, and hence production of electricity. Salt bridges usually come in two types: glass tube and filter paper. Glass tube bridges. One type of salt bridge consists of a U-shaped glass tube filled with a relatively inert electrolyte, usually potassium chloride or sodium chloride, is used. Although the diagram here illustrates the use of a potassium nitrate solution, the electrolyte is so chosen that it does not react with any of the chemicals used in the cell. The anion and cation have similar conductivity, and hence similar migratory speed. The electrolyte is often gelified with agar-agar to help prevent the intermixing of fluids which might otherwise occur. The conductivity of a glass tube bridge depends mostly on the concentration of the electrolyte solution. At concentrations below saturation, an increase in concentration increases conductivity. Beyond saturation, electrolyte content and narrow tube diameter may both lower conductivity. Filter paper bridges. The other type of salt bridge consists of a filter paper, also soaked with a relatively inert electrolyte, usually potassium chloride or sodium chloride because they are chemically inert. No gelification agent is required as the filter paper provides a solid medium for conduction. Conductivity of this kind of salt bridge depends on a number of factors: the concentration of the electrolyte solution, the texture of the filter paper and the absorbing ability of the filter paper. Generally, smoother texture and higher absorbency equates to higher conductivity. A porous disc or other porous barrier between the two half cells may be used instead of a salt bridge, however, they basically serve the same purpose. Uses: as electrons leave one half of a galvanic cell and flow to the other, a difference in electrostatic potential is built up. If no salt bridge were used, this increasing electrostatic potential difference would counteract the electrochemical potential difference and eventually prevent further net flow of electrons. A salt bridge allows the flow of ions to maintain a balance in charge between the oxidation and reduction vessels while keeping the contents of each separate. With the charge difference balanced, electrons can flow once again, and the reduction and oxidation reactions can proceed. In general, keeping the two cells separate is preferable from the point of view of eliminating variables from an experiment. When no direct contact between electrolytes is allowed, there is no need to make allowance for possible interactions between ionic species. The technique more specifically allows freedom in the choice of ions in solution. For instance, a mixture of two different cations in solution might result in the preferential reduction of the wrong one. For the purposes of the experiment with a salt bridge, the desired cation species is isolated in one vessel while the cation in the other vessel may be chosen to make the experiment easier, such as using a more soluble or more stable salt of the anionic species. If the two vessels are entirely disconnected, without a salt bridge, then the cation and anion species are also isolated. But then each species quickly reaches equilibrium because no electric current can flow. The salt bridge can be seen as a way of completing the ionic circuit without letting the solutions intermix. A salt bridge connects the two solutions of half cells. Therefore, it completes the circuit and maintains the electrical neutrality of the two half-cell solutions.
So guys, before going to the electrode potential, I would like to ask you a question. What is the question, sir? When does potential arises? Are you getting my point? When does potential arises? For example, if I say when does electrical potential arises, if I am going to say particularly what type of a potential, when does an electrical potential arises? Since you have come across with your physics classes, you should know what do you mean by current, what do you mean by potential, what do you mean by volt, how you're going to measure it. All these concepts, I think, that has been cleared in physics. I am asking you one basic question. Even though if you have not learnt in second PUC, you have learnt in your lower classes. Yavaga one potential arise agutte. Electric potential yavaga arise agutte. Yes, whenever there is a change or whenever there is a difference in the charges. Alva? Yavatte one potential arise agbekonde artha enu, there should be a difference in the charges. Hangandre artha enu sir? Positive matte negative anta bandaga yenagutte, always there will be a difference in the charges. Avage enagutte ಒಂದು potential arise ಆಗುತ್ತೆ. ಅದೇ ರೀತಿ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಅಲ್ಲಿ ಕೂಡ ಒಂದು ಜಾಸ್ತಿ ಇನ್ನೊಂದು ಕಮ್ಮಿ ಇದ್ರೂ ಕೂಡ ಅಲ್ಲೇನಾಗುತ್ತೆ ಪೊಟೆನ್ಷಿಯಲ್ ಅರೈಸ್ ಆಗುತ್ತೆ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಡ್ಯಾಮ್ ವಾಟರ್ನೇ ತಗೊಳ್ಳಿ. ಡ್ಯಾಮ್ ವಾಟರ್ ಏನ್ ಸ್ಟೋರ್ ಆಗಿದೆ ಗೇಟ್ ಹಿಂದ್ಗಡೆ, ಅದ್ರ ಪೊಟೆನ್ಷಿಯಲ್ ಏನಾಗಿರುತ್ತೆ ಜಾಸ್ತಿ ಇರುತ್ತೆ ಕಂಪೇರ್ ಟು ದಿ ವಾಟರ್ ವಿಚ್ ಇಸ್ ಬಿಲೋ ಅಲ್ವಾ. ಅದೇ ರೀಸನ್ ಇಂದ ಯಾವಾಗ ಅದು ಕೆಳಗೆ ಬೀಳುತ್ತೆ ಆ ಪೊಟೆನ್ಷಿಯಲ್ ಏನಾಗುತ್ತೆ, ದಟ್ ಪೊಟೆನ್ಷಿಯಲ್ ಎನರ್ಜಿ ಇಸ್ ಕನ್ವರ್ಟೆಡ್ ಟು ಯುವರ್ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಅಂತ ತಾನೇ ನೀವು ಇಲ್ಲಿವರೆಗೂ ಓದ್ತಾ ಬಂದಿರೋದು. ಯಾಕೆ ಆತರ? ಬಿಕಾಸ್ ವೆನ್ ಎವರ್ ದೇರ್ ಇಸ್ ಅ ಡಿಫರೆನ್ಸ್ ಆಫ್ ಸಮಥಿಂಗ್, if for example dam water ತಗೊಂಡ್ರೆ there is a difference of height, ಅದೇ ರೀತಿ ನಮ್ಮ electrical potential ತಗೊಂಡ್ರೆ there is a difference in the charges. So whenever there is a difference in the charges, what happens? Always there will be a availability of your, or we can say there will be a generation of potential. Okay, so why you're saying this at this interval of time? Because in order to understand this electrode potential, you should get to know that what do you mean by a potential. Of course, by the word to word meaning, you're going to get that what are the topic we are going to cover in this electrode potential. So something you're getting a hint that we are going to deal with a potential which is associated with the electrode. Alva? Potential which is associated with the electrode. But along with that, you'll be getting a big question mark. Okay, sir, we are getting a potential in the electrode, but where there is a charge difference? Alva? Yelli namge charge difference untalli. Okay, better. We have asked a good question. Now for example, if I just take a half cell of zinc dipped in a zinc sulfate. Zinc dipped in a zinc sulfate. Enu madila, enu external wire hakila nanu. Just what I did, this is your zinc rod which is dipped in a zinc sulfate solution. As we know, your zinc will getting into the zinc sulfate solution as Zn2+. Alva, yen zinc itto electrodo, that is going into the solution as Zn2+. So when it has to go into the solution as Zn2+, what it should leave back in the electrode? Electrons. It has to leave back what? Electrons. I hope so most of you have come to know where does your electrode is getting the potential. Now also if you have not come to know, I am going to explain this, don't worry. Of course, as I mentioned, whenever there is a charge difference, there will be an existence of a potential. So of course we are seeing that your Zn2+ is a positively charged, whereas the electron is what? Negatively charged. So there it develops a potential. So even the potential in generate ಆಗ್ತಾ ಉಂಟಲ್ಲ, this potential itself is called as what? Electrode potential. It is called as what? Electrode potential. So how can I define it? Alva? So the potential difference, yes, developed between the electrode and the electrolyte. The potential difference developed between the electrode and the electrolyte is itself is called as what? Electrode potential, alva. So idenidu zinc electrode, idenidu zinc sulfate electrolyte. ಸೊ ಇವು ಎರಡು ಇಂಟರ್ಫೇಸ್ ಮಧ್ಯದಲ್ಲಿ ಏನೋ ಒಂದು ಪೊಟೆನ್ಶಿಯಲ್ ಡೆವಲಪ್ ಆಗ್ತಾ ಉಂಟಲ್ಲ, ಆ ಪೊಟೆನ್ಶಿಯಲ್ ನಾವೇನಂತ ಹೇಳೋದು? ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಶಿಯಲ್. ಆರ್ ಯು ಏಬಲ್ ಟು ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್? ಸಿಮಿಲರ್ಲಿ ವಿತ್ ರೆಸ್ಪೆಕ್ಟ್ ಟು ಕಾಪರ್ ಕೂಡ, ಕಾಪರ್ ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ, SO4 2- ಹೊರಗಡೆ ಇರುತ್ತೆ, Cu ಒಳಗಡೆ ಇರುತ್ತೆ. ಅಲ್ಲೂ ಕೂಡ ಏನಾಗ್ತಾ ಉಂಟು, ದೇರ್ ವಿಲ್ ಬಿ ಎ ಚಾರ್ಜ್ ಡಿಫರೆನ್ಸ್, ಅಲ್ಲೂ ಕೂಡ ಪೊಟೆನ್ಶಿಯಲ್ ಡೆವಲಪ್ ಆಗುತ್ತೆ. ಸೊ ಆ ಒಂದು ಪೊಟೆನ್ಶಿಯಲ್ ನಾವೇನಂತ ಹೇಳ್ತೀವಿ? ಇಟ್ ಈಸ್ ಅನ್ ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಶಿಯಲ್. ವೈ? Because it is the potential which has been generated between the electrode and the electrolyte. Again and again I'm focusing on my words, guys, because one more potential you're going to see which is called as a cell potential. It will be completely different. So what we are talking now, for that is the reason you just pay attention to my words. Electrode potential andre enu? It is the potential difference which is developed between the electrode and the electrolyte. And the example is lying in before your eyes. Zinc electrodes dipped in a zinc sulfate alli enagta untu, zinc is getting dissolved and going into the solution as Zn2+, leaving behind the electrons. Since there is a charge separation between the electrode and the electrolyte, there will be existence of a potential. So that potential itself will be called as what? Electrode potential. Electrode potential. But in case if I want standard electrode potential, what should I do? How can I get it? Very much important over here. Standard anta bandkule gottagbidbeku, standard conditions na maintain ಮಾಡ್ತೀವಿ. ಏನು standard conditions? Of course ಇಲ್ಲಿವರೆಗೆ same electrode potential as usual, the same definition. Standard ಅಂದಾಗ ಏನಾಗುತ್ತೆ, whatever the potential difference which is going to develop between the electrode and the electrolyte, when the concentration of the solution is unity. Andre I am just taking a 1 molar of my concentration. Any zinc sulfate untala idu nanu 1 molar na consider ಮಾಡಿ, temperature na 298 Kelvin ಅಲ್ಲಿ maintain ಮಾಡಿ, pressure na 1 bar ಅಲ್ಲಿ maintain ಮಾಡಿದಾಗ ಯಾವ potential difference ಹಂಗೆ ಸಿಗುತ್ತೋ ಅದನ್ನೇ ನಾನು ಏನಂತ ಹೇಳ್ತೀವಿ? Standard electrode potential. Getting my point? Again I am going to say, remember, standard electrode potential and the potential difference developed between the electrode and the electrolyte when the concentration of the solution is maintained unity, maintaining a temperature at a 298 Kelvin at a 1 bar atmospheric pressure. So that potential difference is called as what? Standard electrode potential. Very much important topic, because our next videos will be completely dependent upon this topic itself. Is that clear? Remember guys, whenever we say about a standard electrode potential, of course there exists a doubt in us. What is that doubt, sir? Zinc eno Zn agi Zn2+ ಆಗ್ತಾ ಉಂಟು. So this is what? Oxidation. Zn ididu Zn2+. So what is this? Standard oxidation electrode potential or the standard oxidation potential. Copper na consider ಮಾಡಿದ್ರೆ standard reduction potential. ಆದ್ರೆ ಸರ್ ನೀವು ಹೇಳ್ತಾ ಇರೋದು ಬರೀ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಶಿಯಲ್ ಅಲ್ವಾ? ಹಾಗಾದ್ರೆ ನಾವು ಯಾವ್ದನ್ನ ಕನ್ಸಿಡರ್ ಮಾಡಬೇಕು? ಈ ತರ ಒಂದು ಡೌಟು ನಮ್ಮ ಕೆಮಿಸ್ಟ್ರಿ ಅವರಿಗೂ ಬಂತು. ಸೊ ದೇ ಹ್ಯಾವ್ ಅಕಾರ್ಡಿಂಗ್ ಟು ದಿ IUPAC ಪ್ರಕಾರ ಅವ್ರು ಏನ್ ಮಾಡಿದ್ರು, whenever you are coined with the term of standard electrode potential, guys remember, very much important, always you have to consider the standard reduction potential. Always we have to consider as what? Standard reduction potential. ಹಾಗಾದ್ರೆ ಅರ್ಥ ಏನು ಸರ್ ಇದ್ರದ್ದು? ಯಾವತ್ತೇ ಆಗ್ಲಿ ನಿಮ್ಗೆ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಶಿಯಲ್ ಕೊಟ್ಟಿದ್ದಾರೆ ಅಂದ್ರೆ ಅರ್ಥ ಇಟ್ ಇಸ್ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ರಿಡಕ್ಷನ್ ಪೊಟೆನ್ಶಿಯಲ್ ಆಫ್ ದಟ್ ಎಲೆಕ್ಟ್ರೋಡ್. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಜಿಂಕಿಗೆ ಏನೋ ಒಂದು ಪೊಟೆನ್ಶಿಯಲ್ ನ ಕೊಟ್ಟಿದ್ದಾರೆ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಏನೋ y ವೋಲ್ಟ್ ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ ಅಂತ ತಿಳ್ಕೊಳ್ಳೋಣ. ಓಕೆ, ಈ y ವೋಲ್ಟ್ ಅಂದ್ರೆ ಅಫ್ಕೋರ್ಸ್ ಡಿನೆಲ್ಸಲ್ ಪ್ರಕಾರ ಏನಂತ ಅರ್ಥ ನಮಗೆ ಗೊತ್ತಿದ್ದು, ಜಿಂಕ್ ಆಲ್ವೇಸ್ ಅಂಡರ್ಗೋಸ್ ಆಕ್ಸಿಡೇಷನ್ ಅಲ್ವಾ? ಅದಕ್ಕೆ ಏನೋ ಒಂದು ವ್ಯಾಲ್ಯೂ ಬಂದಿರುತ್ತೆ. ಆದ್ರೆ ನಿಮಗೆ ನಿಮಗೆ ಯಾವತ್ತೇ ಒಂದು ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಜಿಂಕ್ ಈಸ್ ಹ್ಯಾವಿಂಗ್ y ವೋಲ್ಟ್ ಆಫ್ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಷಿಯಲ್ ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ ಅಂದ್ರೆ ಅರ್ಥ ಯು ಶುಡ್ ಗೆಟ್ ರಿಮೆಂಬರ್ ದಟ್ ಇಟ್ ಈಸ್ ನಾಟ್ ಅನ್ ಆಕ್ಸಿಡೇಷನ್ ಪೊಟೆನ್ಷಿಯಲ್ ವೆರ್ ಆಸ್ ಇಟ್ ಈಸ್ ಅ ರಿಡಕ್ಷನ್ ಪೊಟೆನ್ಷಿಯಲ್. ದಟ್ ಮೀನ್ಸ್ ವಾಟ್, ಜಿಂಕ್ ಇರೋದು ಅಥವಾ ಜಿಂಕ್ ಅಯಾನ್ ಇರೋದು 2 ಎಲೆಕ್ಟ್ರಾನ್ ತಗೊಂಡಾಗ ಏನ್ ಪೊಟೆನ್ಷಿಯಲ್ ಬಂತು ಅನ್ನೋದನ್ನ ನಿಮಗೆ ಕೊಟ್ಟಿದ್ದಾರೆ ಅಂತ ಅರ್ಥ ಅಲ್ವಾ. ಗೇನಿಂಗ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ ಇಟ್ ಸೆಲ್ಫ್ ಇಸ್ ಕಾಲ್ಡ್ ಆಸ್ ವಾಟ್, ರಿಡಕ್ಷನ್. ಆ ರೀಸನ್ ಇಂದಾನೆ ಹೇಳ್ತಿರೋದು. ಯಾವತ್ತೇ ಆಗ್ಲಿ ನಿಮ್ಮ ಪೇಪರ್ ಅಲ್ಲಿ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಎಲೆಕ್ಟ್ರೋಡ್ ಪೊಟೆನ್ಷಿಯಲ್ ಕೊಟ್ಟಿದ್ದಾರೆ ಅಂದ್ರೆ ಅರ್ಥ ಏನು, ಇಟ್ ಇಸ್ ಆಲ್ವೇಸ್ ಅ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ರಿಡಕ್ಷನ್ ಪೊಟೆನ್ಷಿಯಲ್. ಹಂಗಂದ್ರೆ ಅರ್ಥ ಏನು, ಆ ಒಂದು ಎಲೆಕ್ಟ್ರೋಡ್ ಎಲೆಕ್ಟ್ರಾನ್ ಗೇನ್ ಮಾಡಿದಾಗ ಎಷ್ಟು ಪೊಟೆನ್ಷಿಯಲ್ ಬಂತು ಅನ್ನೋದನ್ನ ನಾವೇನಂತ ಹೇಳ್ತೀವಿ ಇನ್ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಕಂಡೀಷನ್, ಅದನ್ನ ನಾವೇನಂತ ಹೇಳ್ತೀವಿ, ಸ್ಟ್ಯಾಂಡರ್ಡ್ ರಿಡಕ್ಷನ್ potential. Okay, are you able to understand? Very much important. Again, I am saying, according to the IUPAC, your standard reduction potential is always considered as a standard electrode potential. Utilizing this concept itself, we will be seeing the series, which itself is called as an electrochemical series, which will be dealt in my next video completely. Okay, but before that one, you have to understand certain concepts. Able to understand? No problem. Further, when we go with the further classes, better understanding, you will be going to understand in a better way. Similarly, ಈಗ ನಮಗೆ ಆನೋಡ್ ಅಂದ್ರೆ ಏನು, ಕ್ಯಾಥೋಡ್ ಅಂದ್ರೆ ಏನು ಅನ್ನೋದು ಗೊತ್ತಾಗಬೇಕು ಅಲ್ವಾ. ಇಲ್ಲಿವರೆಗೆ ನಾವು ಎಲೆಕ್ಟ್ರೋಡ್ಸ್ ಅಂತ ಯೂಸ್ ಮಾಡ್ತಾ ಇದ್ವಿ. ಆನೋಡ್ ಅಂದ್ರೆ ಏನು, ಕ್ಯಾಥೋಡ್ ಅಂದ್ರೆ ಏನು ಅಂತ ಕೂಡ ಐಯುಪ್ಯಾಕ್ ನಮಗೆ ಒಂದು ಹಿಂಟ್ ಕೊಡುತ್ತೆ. ಏನದು ಹಿಂಟು? ಸೊ ಆನೋಡ್ ಅಂದ್ರೆ ಇನ್ ಅ ಗ್ಯಾಲ್ವಾನಿಕ್ ಸೆಲ್. ರಿಮೆಂಬರ್, ಇನ್ ಅ galvanic cell. I am only particular about my cell. I am using my galvanic cell. So in a galvanic cell, the half cell in which oxidation takes place, so that electrode is called as what? Anode. So that electrode in which the oxidation is taking place. In a galvanic cell, the half cell in which the oxidation takes place, that electrode is called as what? Anode. Similarly, cathode, in a galvanic cell, a half cell in which reduction takes place, that electrode is called as what? That electrode is called as your cathode. That electrode is called as cathode. Many times I have said this. How to remember this? Of course, in Karnataka, everybody's favorite team is RCB, Royal Challengers Bangalore. But I don't know whether this time they will gain the trophy or not. That is a different task for us. But according to chemistry, I'm going to use this IPL's team RCB to my chemistry as RCB. It is not Royal Challengers Bangalore. According to my chemistry, it is reduction at the cathode body. ಅಲ್ವಾ. ಈಗ ನೀವು ಜ್ಞಾಪಕ ಇಟ್ಕೋಬಹುದಲ್ವಾ, ಕ್ಯಾಥೋಡ್ ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ, ರಿಡಕ್ಷನ್ ಆಗುತ್ತೆ. ಇದು ಕನ್ಫ್ಯೂಸಿಂಗ್ ಇರಬಹುದು, ಆದ್ರೆ RCB ಯಾವುದು ಕನ್ಫ್ಯೂಸಿಂಗ್ ಅಲ್ಲ, ಬಿಕಾಸ್ ಇಟ್ಸ್ ಅವರ್ ಫೇವರೆಟ್ ಟೀಮ್. ಅಫ್ಕೋರ್ಸ್ ಇಟ್ ಇಸ್ ನಾಟ್ ಆಫ್ ಮೈನ್ is Mumbai Indians, different task. But most of you, Karnataka always lies RCB. For that is the reason I'm just giving you this hint. RCB means reduction at the cathode body. Similarly, to call someone, how will you call who is familiar to OA? We call it someone as OA. Come here. So OA, that means what? Oxidation at anode. Easy ಅಲ್ಲ, ಯಾವ್ದಾದ್ರು ಒಂದು ಜ್ಞಾಪಕ ಇಟ್ಕೊಳ್ಳಿ. RCB, I think it's common for everyone, you can remember it. Reduction at cathode body. ಏನಂತ ಹೇಳ್ತೀವಿ? ರಿಡಕ್ಷನ್ ಅಟ್ ಕ್ಯಾಥೋಡ್ ಬಾಡಿ. ಏನು ರಿಡಕ್ಷನ್ ಅಂದ್ರೆ, ಅಫ್ ಕೋರ್ಸ್ ಯು ನೋ, ರಿಡಕ್ಷನ್ ಮೀನ್ಸ್ ಗೇನ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್. ಅದೇ ರೀತಿ ಆಕ್ಸಿಡೇಷನ್ ಮೀನ್ಸ್ ವಾಟ್? ಲಾಸ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್. ಈಗ ಸದ್ಯಕ್ಕೆ ನಾನು ಆಕ್ಸಿಡೈಸಿಂಗ್ ಏಜೆಂಟ್ ಮತ್ತೆ ರೆಡ್ಯೂಸಿಂಗ್ ಏಜೆಂಟ್ ನ ಹೇಳಲ್ಲ, ಯಾಕಂದ್ರೆ ಕನ್ಫ್ಯೂಷನ್ ಆಗಬಾರ್ದು. ನೀವು ಫಸ್ಟ್ ನೀವು ರಿಡಕ್ಷನ್ ಅಂದ್ರೆ ಏನು, ಆಕ್ಸಿಡೇಷನ್ ಅಂದ್ರೆ ಏನು ಕಂಪ್ಲೀಟ್ ಆಗಿ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿ. ರಿಡಕ್ಷನ್ means gaining of electrons. Oxidation means ಲಾಸ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ವಿತ್ ರೆಸ್ಪೆಕ್ಟ್ ಟು ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ನಾನು ರೆಡಾಕ್ಸ್ ಅಲ್ಲಿ ಸುಮಾರು ಸರಿ ಹೇಳಿದ್ದೀನಿ ಇದನ್ನ. ಓಕೆ, ಕನ್ಫ್ಯೂಷನ್ ಇರಬಾರ್ದು ನಿಮ್ಗೆ, ಇದ್ರೂ ಕೂಡ ಈಗಲೇ ಕ್ಲಿಯರ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಬಿಕಾಸ್ ಈ ಕಾನ್ಸೆಪ್ಟ್ ಗಳು ತುಂಬಾನೇ ಇಂಪಾರ್ಟೆಂಟ್ ನಮಗೆ. ಲೇಟರ್ ಬರೋ ಎಲ್ಲಾ ವಿಡಿಯೋಸ್ ಅಲ್ಲೂ ಈ ಕಾನ್ಸೆಪ್ಟ್ ನಾವು ಯೂಸ್ ಮಾಡ್ಕೊಂಡೆ ಮುಂದೆ ಹೋಗ್ತೀವಿ. ಇನ್ನೊಂದ್ಸರಿ ಹೇಳ್ತಾ ಇದೀವಿ, ರಿಡಕ್ಷನ್ ಮೀನ್ಸ್ ಗೇನ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ which takes place where? At the electrode, which is called as cathode. Oxidation means loss of electrons which takes place at the electrode, which is called as what? Anode. Very much important. Okay, how to remember? RCB, reduction at the cathode body. OA, oxidation at anode. Is that clear? I hope so. There is no doubt in it. Can we move further then? Okay. So guys, when I was explaining about an electrode potential, of course I do mention that potential always arises whenever there is a charge difference. I think most of you can get a question over here. Okay sir, you consider a beaker, a single beaker in which you have dipped a zinc rod in a zinc sulfate or a respective electrode in the respective electrolytic solution. There was a potential difference. But what about you consider the whole cell? For example, the Daniell cell. Of course, illige enagutte zinc is, of course, zinc and copper both will be existing. ಯಾವುದು ಒಂದ್ ಕಡೆ ಏನಾಗಿರುತ್ತೆ ಪಾಸಿಟಿವ್ ಇರುತ್ತೆ, ಇನ್ನೊಂದ್ ಕಡೆ ಏನಾಗಿರುತ್ತೆ ನೆಗೆಟಿವ್ ಇರುತ್ತೆ ಅಲ್ವಾ. ಆಫ್ ಕೋರ್ಸ್ ಆನೋಡ್ ಮತ್ತೆ ಕ್ಯಾಥೋಡ್ ಇದ್ದೇ ಇರುತ್ತೆ. ಸೊ ದೇರ್ ಇಸ್ ಆಲ್ಸೋ ಅ ಪೊಟೆನ್ಶಿಯಲ್ ಡಿಫರೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದಿ ಟೂ ಎಲೆಕ್ಟ್ರೋಡ್ಸ್. Remembering my words, that is the reason I said electrode potential was what? The potential difference which is developed between the electrode and the electrolyte. But when you consider the whole cell, there is also a potential difference between the two electrodes. Of course, this is also a potential. Then what? Whether we are going to measure it or not? Of course, we are going to measure it, and that measurement itself is called as what? Cell potential. Are you able to see? This was what? Electrode potential, whereas this is called as what? Cell potential. So how can you define the cell potential? The potential difference developed between the two electrodes of a galvanic cell is called as what? Cell potential. Getting my point? Very much important, because it is having a formula in which you can, by the given values of your reduction potentials or the standard electrode potential, we can calculate the EMF of a cell, which will be dealt in my next video. But the formula is very much important. Cell potential andre, it's a potential difference developed between the two electrodes of a galvanic cell. It is called as cell potential. In certain scenarios, it is also called as EMF. Most of you know it. Electromotive force. What it is called as? Electromotive force. And it's always measured in volts. Of course, potential difference means it's always measured in volts itself. So cell potential na navu enanta heltivi? Electromotive force antanu heltivi. And the formula is E cell, very much what you can say, comedy. I can say you can get a smile on your face by seeing the formula, because E cell is equals to, I will be writing it as E right minus E left. E right minus E left. Of course, two emojis will be now in your brain. One emoji will be like this. Another emoji will be somewhat like this. This means what? You are having a doubt in it. What is the doubt? This smile was of course common because you are getting something which is not known to you. Right, left, and sir. What, we are doing something soldier march? Of course not. This emoji is, there is a bit confusing, or we can say that there is a doubt. What do you mean by right and what do you mean by left? So in order to understand what do you mean by this right and what do you mean by this left, you have to understand one concept over here. What is that concept? How to write the galvanic cell symbolically. ಅಲ್ವಾ? ಯಾಕೆ ಇದನ್ನ ಸಿಂಬಾಲಿಕಲ್ ಈಗ ರಿಪ್ರೆಸೆಂಟ್ ಮಾಡಬೇಕು? ಯಾಕಂದ್ರೆ ಎಲ್ಲಾ ಟೈಮ್ ನಾನು ಬೀಕರ್ ನ ಬರ್ದಿ, ಎಲೆಕ್ಟ್ರೋಡ್ ನ ಬರ್ದಿ, ಸರ್ಕ್ಯೂಟ್ ನ ಬರ್ದಿ, ಸಾಲ್ಟ್ ಬ್ರಿಡ್ಜ್ ನ ಬರೆಯಕ್ ಆಗೋದಿಲ್ಲ. ಇನ್ ಆರ್ಡರ್ ಟು ಅವಾಯ್ಡ್ ದಿಸ್, IUPAC has given us a notation, a symbolical rotation to how to write this galvanic cell. So pay attention. So it is written in this way: metal, solid, single bar, metal, ion, aqueous, double bar, metal ion aqueous single bar metal solid. Confusing, huh? Don't worry. At the instant of time, this confusion will be vanished from your head. First of all, let us understand the importance of these bars. Okay, these bars. Guys, boys, don't think of another bar. I'm just talking about this bar. Okay. First of all, it is your single bar. Single bar andre ee single line in hakidina. What are the importance of this? So remember, single bar represents your electrode and an electrolyte interface. Electrode and the electrolyte interface. Hangadre artha enu sir? For example, zinc dipped in zinc sulfate. Zinc rod zinc sulfate in a ಏನ್ ಇಂಟರ್ಫೇಸ್ ಇವೆರಡನ್ನು ಡಿಸ್ಟಿಂಗ್ವಿಶ್ ಮಾಡಲೇಬೇಕಲ್ವಾ? ಆ ಡಿಸ್ಟಿಂಗ್ವಿಶ್ ಯಾವ್ದು ಮಾಡುತ್ತೆ? ಸಿಂಗಲ್ ಬಾರ್. ಇಲ್ಲೂ ಕೂಡ ಅದೇ ಎಲೆಕ್ಟ್ರೋಲೈಟ್ ಎಲೆಕ್ಟ್ರೋಡ್. ಓಕೆ, ಹಾಗಾದ್ರೆ ಡಬಲ್ ಬಾರ್ ಏನಿದು? ಅಫ್ಕೋರ್ಸ್ ನಾವು ಡಬಲ್ ಅಂತ ಎಲ್ಲಿ ಬರ್ದಿದ್ವಿ ಒಂದು ಸ್ವಲ್ಪ ಯೋಚನೆ ಮಾಡಿ. ಡಬಲ್ ಸ್ಟ್ರಾಂಡ್ ಹಂಗೆ. ಎಸ್, it indicates your salt bridge. It indicates your salt bridge. It doesn't stop over here. ಇಲ್ಲೂ ಎಂ ಬರ್ದಿದ್ದೀನಿ, ಇಲ್ಲೂ ಎಂ ಬರ್ದಿದ್ದೀನಿ. ಅಫ್ಕೋರ್ಸ್ ಒಂದು ಸೆಲ್ ನ ಕನ್ಸಿಡರ್ ಮಾಡಬೇಕು ಅಂದ್ರೆ ಒಂದ್ ಕಡೆ ಕ್ಯಾಥೋಡ್, ಇನ್ನೊಂದ್ ಕಡೆ ಆನೋಡ್. ಈಗ ಕ್ವಶನ್ ಅರೈಸ್ ಆಗೋದು, ಎಲ್ಲಿಗೆ ಕ್ಯಾಥೋಡ್ ಬರುತ್ತೆ ಅಥವಾ ಯಾವ್ದಿಗೆ ಇಲ್ಲಿ ಆನೋಡ್? ಇಲ್ಲಿ ನೀವು ಕರೆಕ್ಟ್ ಆಗಿ ನೋಡಿದ್ರೆ ನೀವಾಗೆ ಹೇಳ್ಬಹುದು ಏನಂತ. ಮೆಟಲ್ ಇದಿದ್ದು ಮೆಟಲ್ ಅಯಾನ್ ಕನ್ವರ್ಟ್ ಆಗ್ತಾ ಉಂಟು, ಮೆಟಲ್ ಅಯಾನ್ ಇರಿದು ಮೆಟಲ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತಾ ಉಂಟು ಅಲ್ವಾ? ಅದೇ ರೀತಿಲಿ ಹೋಗ್ತಾ ಫ್ರಮ್ ಯುವರ್ ಲೆಫ್ಟ್ ಟು ರೈಟ್ ವಿ ಆರ್ ಗೋಯಿಂಗ್. ಮೆಟಲ್ ಇದ್ದಿದ್ದು ಮೆಟಲ್ ಅಯಾನ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತಾ ಉಂಟು, ಮೆಟಲ್ ಅಯಾನ್ ಇರೋದು ಮೆಟಲ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತಾ ಉಂಟು. ದಟ್ ಮೀನ್ಸ್ ವಾಟ್? ಅಟ್ ದಿ ಎಕ್ಸ್ಟ್ರೀಮ್ ಎಂಡ್ಸ್, ಏನಿ ಎಕ್ಸ್ಟ್ರೀಮ್ ಎಂಡ್ಸ್ ಉಂಟಲ್ಲ, ಅಫ್ಕೋರ್ಸ್ ಇಟ್ ಇಂಡಿಕೇಟ್ಸ್ ಯುವರ್ ಎಲೆಕ್ಟ್ರೋಡ್. ಆದ್ರೆ ಆಟ್ ಲೆಫ್ಟ್ ಮೋಸ್ಟ್ ಪಾರ್ಟ್, ಅಟ್ ದಿ ಲೆಫ್ಟ್ ಎಕ್ಸ್ಟ್ರೀಮ್ ಎಂಡ್ ಏನುಂಟಲ್ಲ, that represents your oxidation electrode. That represents your what? Oxidation electrode. That means what? Oxidation ಆಗೋದಲ್ಲಿ anode. So left ಅಲ್ಲಿ ನಾವೇನ್ ಬರಿತೀವಿ? Anode. ಅದೇ ರೀತಿ at the extreme right, that is this part, it represents what? Your reduction electrode. It represents what? Reduction electrode. That means what? Cathode. It represents your cathode. You getting my point? For example, ಈಗ ಇನ್ನೊಂದು ಸರಿ ನೋಡೋಣ. M bar Mn plus aqueous, N plus ಅಂದ್ರೆ number of the electrons it is losing or gaining. Double bar means salt bridge. Mn plus once again the aqueous solution में what type of ion it is having. Afterwards M. So whatever the single bar is there, it represents your electrode electrolyte interface. Double bar salt bridge. Left at the extreme ends, of course, they are the electrodes. At the left extreme part, it represents your oxidation electrode, which means anode. At the right extreme part, it represents your reduction electrode, which means cathode. Is that clear? Okay. Now let us go with my formula. E cell equals to E right minus E left. ಈಗ ಅರ್ಥ ಆಯ್ತಾ ಯಾಕೆ ರೈಟ್ ಯಾಕೆ ಲೆಫ್ಟ್ ಅಂತ? ರೈಟ್ ಅಂದ್ರೆ ಏನು? You have to measure the standard electrode potential of the cathode. So we required over here as this could be also written as what? Of course this is not followed. For my convenience, when I was in second PUC, ಈ ರೈಟ್ ಲೆಫ್ಟ್ ಒಂದು ಸ್ವಲ್ಪ ನಂಗೆ ಕನ್ಫ್ಯೂಷನ್ ಆಗ್ತದೆ. ಸೊ ನಾನು ಏನಂತ ಬರ್ಕೊಂಡೆ, ಈ ಕ್ಯಾಥೋಡ್ ಮೈನಸ್ ಈ ಆನೋಡ್. You can also write, don't write it, okay? Just for your convenience, if you want, if you can remember in this way, you can remember. E cathode minus E anode. Otherwise you can remember in this way also, right left when you do the march fast, left right ಅಂತ ಹೇಳ್ತಾರೆ, ಅದು ಇಲ್ಲಿ ಉಲ್ಟಾ ಆಗಿ ನೀವು ಜ್ಞಾಪಕ ಇಟ್ಕೋಬೇಕು. ಸೊ ಆ ಕನ್ಫ್ಯೂಷನ್ ಬೇಡ ಅಂತಾನೆ E cathode minus E anode. Is that clear? So you have to measure the standard electrode potential, that means standard reduction potential of the cathode. Then you have to measure the standard reduction potential of the anode. ಈ ಒಂದು ಫಾರ್ಮುಲಾದಲ್ಲಿ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಇದಕ್ಕೂ ನೀವು ಆಕ್ಸಿಡೇಷನ್ ತಗೊಂಡ್ರೆ ಇದಕ್ಕೂ ನೀವು ಆಕ್ಸಿಡೇಷನ್ ತಗೋಬೇಕು, ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಆಕ್ಸಿಡೇಷನ್ ಪೊಟೆನ್ಷಿಯಲ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಬೇಕು. ಎಲ್ಲಾರು ಒಂದಕ್ಕೂ ನೀವು ಸ್ಟ್ಯಾಂಡರ್ಡ್ ರಿಡಕ್ಷನ್ ಪೊಟೆನ್ಷಿಯಲ್ ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತಿದ್ದೀರಾ ಅಂದ್ರೆ ಇನ್ನೊಂದಕ್ಕೂ ಏನ್ ಮಾಡಬೇಕು? ಸ್ಟ್ಯಾಂಡರ್ಡ್ ರಿಡಕ್ಷನ್ ಪೊಟೆನ್ಷಿಯಲ್ ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಬೇಕು. ಅದು ಯಾವ ತರ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡಿದ್ರು ಪ್ರಾಕ್ಟಿಕಲ್ ಅಲ್ಲಿ, ದಟ್ ವಿಲ್ ಬಿ ಸೀನ್ ಇನ್ ದಿ ನೆಕ್ಸ್ಟ್ ವಿಡಿಯೋ. ಈಗ ಬರೀ ಕಾನ್ಸೆಪ್ಟ್ ನ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿ. ಯಾವತ್ತೇ ನೀವು ಇಲ್ಲಿ ಒಂದು ಪೊಟೆನ್ಷಿಯಲ್ ವ್ಯಾಲ್ಯೂಸ್ ನ ಹಾಕ್ತಿದ್ದೀರಾ ಅಂದ್ರೆ ಆಕ್ಸಿಡೇಷನ್ ತಗೊಂಡ್ರೆ ಆಕ್ಸಿಡೇಷನ್ ಪೊಟೆನ್ಷಿಯಲ್ ತಗೋಬೇಕು, ರಿಡಕ್ಷನ್ ಪೊಟೆನ್ಷಿಯಲ್ ತಗೊಂಡ್ರೆ ರಿಡಕ್ಷನ್ ಪೊಟೆನ್ಷಿಯಲ್ ತಗೋಬೇಕು. Both the potentials should be same with respect to whether they are going oxidation or reduction. Is that clear? Now you got the concept why we have used as a right and left. ಬಿಕಾಸ್ ಈ ಕಾನ್ಸೆಪ್ಟ್ ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕಂದ್ರೆ ಗ್ಯಾಲ್ವ್ಯಾನಿಕ್ ಸೆಲ್ಲಿನ ರೆಪ್ರೆಸೆಂಟೇಷನ್ ನಿಮಗೆ ಬರಬೇಕು. ಈಗ ನಮ್ಮ ಒಂದು ಕ್ವಶನ್ ತಗೊಳ್ಳೋಣ. ಡೇನಿಯಲ್ ಸೆಲ್ ನ ನೀವು ಸಿಂಬಾಲಿಕ್ ಆಗಿ ರಿಪ್ರೆಸೆಂಟ್ ಮಾಡಿ. ಹೆಂಗ್ ಮಾಡ್ತೀರಾ? ಸೊ ಫಸ್ಟ್ ಲೆಫ್ಟ್ ಗೆ ಏನ್ ಬರಬೇಕು? ನಂದು ಸಾಲಿಡ್ ಬರಬೇಕು, ಅಂದ್ರೆ ಎಲೆಕ್ಟ್ರೋಡ್ ಬರಬೇಕು. ಎಲೆಕ್ಟ್ರೋಡ್ ಯಾವ್ದಾಗಿರ್ಬೇಕು? ಆನೋಡ್ ಆಗಿರ್ಬೇಕು. ಆನೋಡ್ ಅಂದ್ರೆ ಏನು? ಆಕ್ಸಿಡೇಷನ್ ಆಗಬೇಕು. ಆಕ್ಸಿಡೇಷನ್ ಅಂದ್ರೆ ಲಾಸ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್. ಸೊ ಯಾವ್ದು ಲಾಸ್ ಆಗ್ತಾ ಉಂಟು ಅಲ್ಲಿ? ಜಿಂಕ್ ಅಲ್ವಾ? ಸಿಂಗಲ್ ಬಾರ್ ಎಲ್ಲಿಗೆ ಹೋಗ್ತಾ ಉಂಟು ಲಾಸ್ ಆಗಿ? Zn2+ ಗೆ ಹೋಗ್ತಾ ಉಂಟು. ಅದ್ಯಾವ್ದು ಇಲ್ಲೋ? ಎಕ್ವೆಸ್ ಅಲ್ವಾ? ಇದಿಷ್ಟು ಒಂದಾಯ್ತು. ಡಬಲ್ ಬಾರ್ ಸಾಲ್ಟ್ ಬ್ರಿಡ್ಜ್ ಮಧ್ಯದಲ್ಲಿ ಬಂತು. ಆ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಹೋಗಿದ್ದು ಎಲ್ಲಿ ಫಸ್ಟ್ ಹೋಗುತ್ತೆ? Cu2+ ಗೆ ಹೋಗ್ಬೇಕು. ಫೈನಲ್ ಆಗಿ ಏನ್ ಬರಬೇಕು ನಂಗೆ? ರೈಟ್ ಅಲ್ಲಿ ರಿಡಕ್ಷನ್ ಎಲೆಕ್ಟ್ರೋಡ್, ದಟ್ ಇಸ್ ಯೋರ್ ಕ್ಯಾಥೋಡ್, ದಟ್ ಇಸ್ ಯೋರ್ ಕಾಪರ್, ವೇರ್ ಇಟ್ ಇಸ್ ಅಂಡರ್ಗೋಯಿಂಗ್ ವಾಟ್? ಗೇನಿಂಗ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್. ಇಲ್ಲ ಒಂದು ಕೆಲಸ ಮಾಡೋಣ, ಇನ್ನೂ ಸುಲಭವಾಗಿ ಹೇಳಬೇಕು ಅಂದ್ರೆ ದಿಸ್ ಇಸ್ ಎಕ್ವೆಸ್, ದಿಸ್ ಇಸ್ ಸಾಲಿಡ್. ಫಸ್ಟ್ ಏನ್ ಮಾಡ್ಕೊಳ್ಳಿ, ಯಾವತ್ತೇ ಒಂದು ಸೆಲ್ ಬರೆಯೋದಾದ್ರು, ಫಾರ್ ಯೋರ್ ಕನ್ವೀನಿಯನ್ಸ್ ಐ ಆಮ್ ಸೇಯಿಂಗ್, ಅಟ್ ದಿ ಎಕ್ಸ್ಟ್ರೀಮ್ ಯು ನೋ ದಟ್ ಎಲೆಕ್ಟ್ರೋಡ್ ಶುಡ್ ಕಮ್. ಸೊ ಫಸ್ಟ್ ಯಾವ್ದು ಬರಬೇಕು? ಲೆಫ್ಟ್ ಕಡೆ ಆನೋಡ್ ಬರಬೇಕು, ಕ್ಯಾಥೋಡ್ ಬರಬೇಕು. ಫಸ್ಟ್ ಬರ್ಕೋಬೇಡೋಣ, ಜಿಂಕ್ ಬರಬೇಕು, ಕಾಪರ್ ಬರಬೇಕು. ಯಾಕಂದ್ರೆ ಎಕ್ಸ್ಟ್ರೀಮ್ ಅಲ್ಲಿ ಯಾವತ್ತೇ ಆಗಲಿ ಎಲೆಕ್ಟ್ರೋಡ್ ಬರಬೇಕು. ಜಿಂಕ್ ಎಲ್ಲಿಗೆ ಹೋಗಬೇಕು? Zn2+ ಗೆ ಹೋಗಬೇಕು. ಮಧ್ಯದಲ್ಲಿ ಸಾಲ್ಟ್ ಬ್ರಿಡ್ಜ್ ಬರುತ್ತೆ. ಕಾಪರ್ ಹೆಂಗ್ ಬಂತು ನಮ್ಗೆ? Cu2+ ಇಂದ ಬಂತು. ಇನ್ ಐದರ್ ವೇಸ್ ಯು ಕ್ಯಾನ್ ಜಸ್ಟ್ ಟೇಕ್ ಅ ಹಿಂಟ್ ಟು ರೈಟ್ ದಿಸ್ symbolically. Is that clear? Are you able to understand, guys? Very much important to know the symbolic representation, because many times they can ask you. So this was the one way of asking, because Daniel cell is common to everyone, so anyone can write it. But I would like to give you one question. For example, if I give you a reaction, Cu solid, and it is giving and is reacting with a 2Ag+, which is aqueous, okay, and it is giving you as a Cu2+, which is also aqueous, and 2Ag, which is solid. And I will asking you to write the galvanic cell symbolically for this overall cell reaction. How are you going to write it? Are you getting my point? I have given you this question in which it consists of overall cell reaction, and I'm asking you to write the galvanic cell symbolically. So whenever you have been given with such question, here comes the concept of your half cells. Half cell ಅಲ್ಲಿ ಎಲ್ಲಿ ಆಕ್ಸಿಡೇಷನ್ ಹಾಫ್ ರಿಯಾಕ್ಷನ್ ಆಗ್ತಾ ಉಂಟು, ಎಲ್ಲಿ ರಿಡಕ್ಷನ್ ಹಾಫ್ ರಿಯಾಕ್ಷನ್ ಆಗ್ತಾ ಉಂಟು ಅಂತ ನೀವು ಅನಲೈಸ್ ಮಾಡಬೇಕು. ಈಗ ಇಲ್ಲಿ ನೋಡಿ, ಕಾಪರ್ ಇದ್ದಿದ್ದು ಕಾಪರ್ ಅಯಾನ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತಾ ಉಂಟು. ಹಾಗಾದ್ರೆ ಅರ್ಥ ಏನು? Cu is losing 2 electrons. That means oxidation. ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಏನಾಗ್ತಾ ಉಂಟು? ಆಕ್ಸಿಡೇಷನ್. ಸಿಮಿಲರ್ಲಿ 2Ag+ ಇರೋದು Ag ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತಾ ಉಂಟು. ದಟ್ ಮೀನ್ಸ್ ವಾಟ್? ಅನಾಲಿಸಿಸ್ ಪ್ರಕಾರ ಇದು ರಿಡಕ್ಷನ್ ಆಗ್ತಾ ಉಂಟು. ಸೊ ಫಸ್ಟ್ ಏನ್ ಮಾಡಿ, ನೀವು ಆ ರಿಯಾಕ್ಷನ್ಸ್ ನ ಬರ್ಕೊಳ್ಳೋಣ. ಫಸ್ಟ್ ಏನ್ ಮಾಡ್ತೀರಿ? Cu ಇದ್ದಿದ್ದು 2 ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ನ ಕಳ್ಕೊಂಡು Cu2+ ಬರ್ತಾ ಉಂಟು. 2Ag+ ಇರೋದು 2 ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ನ ಗೇನ್ ಮಾಡಿ ಏನಾಗ್ತಾ ಉಂಟು? 2Ag ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತಾ ಉಂಟು ಅಲ್ವಾ? ಇದು ಕರೆಕ್ಟ್ ತಪ್ಪು ಅಂತ ಹೆಂಗ್ ಗೊತ್ತಾಗುತ್ತೆ? ಇನ್ನೊಂದ್ಸರಿ ಇದನ್ನು ಡಿಲೀಟ್ ಮಾಡ್ಕೊಂಡು ಎಲ್ಲ ನೀವೇ ಇನ್ನೊಂದ್ಸರಿ ಬರೀರಿ. Cu plus 2Ag+ gives you Cu2+ plus 2Ag, which is similar to the equation what they have given you in question. ಈ ರಿಯಾಕ್ಷನ್ ಬರುತ್ತೆ ಏನ್ ಇಂಪಾರ್ಟೆಂಟು? ಇದೇನಿದು? ಆಕ್ಸಿಡೇಷನ್ ಹಾಫ್ ರಿಯಾಕ್ಷನ್. ಆಕ್ಸಿಡೇಷನ್ ಹಾಫ್ ರಿಯಾಕ್ಷನ್. ಇದೇನಿದು? ರಿಡಕ್ಷನ್ ಹಾಫ್ ರಿಯಾಕ್ಷನ್. ರಿಡಕ್ಷನ್ ಹಾಫ್ ರಿಯಾಕ್ಷನ್. ಆಕ್ಸಿಡೇಷನ್ ಹಾಫ್ ರಿಯಾಕ್ಷನ್ ಎಲ್ಲಾಗುತ್ತೆ? OA, ದಟ್ ಮೀನ್ಸ್ ಆನೋಡ್. ರಿಡಕ್ಷನ್ ಹಾಫ್ ರಿಯಾಕ್ಷನ್ ಎಲ್ಲಾಗುತ್ತೆ? RCB, ಮೀನ್ಸ್ ಕ್ಯಾಥೋಡ್. ಸೊ ಈ ಒಂದು ಹಾಫ್ ರಿಯಾಕ್ಷನ್ ಬರೆದಾಗ ನಿಮ್ಗೆ ಯಾವುದು ಆನೋಡು ಯಾವುದು ಕ್ಯಾಥೋಡು ಅಂತ ಗೊತ್ತಾಗ್ಬಿಡುತ್ತೆ. ಅವಾಗ ನೀವು ಸಿಂಬಾಲಿಕಲಿ ಬರೀಬಹುದಲ್ಲ. ಫಸ್ಟ್ ಏನ್ ಮಾಡಿದ್ರಿ? ಎಕ್ಸ್ಟ್ರೀಮ್ ಎಂಡ್ಸ್ ಅಲ್ಲಿ ಎಲೆಕ್ಟ್ರೋಡ್ ಬರಬೇಕು. ಫಸ್ಟ್ ಯಾವ್ದು ಬರಬೇಕು? ಲೆಫ್ಟ್ ಅಲ್ಲಿ ಆಕ್ಸಿಡೇಷನ್ ಎಲೆಕ್ಟ್ರೋಡ್, ದಟ್ ಮೀನ್ಸ್ ಆನೋಡ್. ಸೊ ನನ್ನ ರಿಯಾಕ್ಷನ್ ಅಲ್ಲಿ ಆನೋಡ್ ಯಾವ್ದೀಗ? ಕಾಪರ್. Cu ಬರ್ದೆ, which is going to single bar, going to as what? Cu2+. ಡಬಲ್ ಬಾರ್ ಏನ್ ಬರ್ಬೇಕೀಗ ಇಲ್ಲಿ? 2Ag+. ಸಿಂಗಲ್ ಬಾರ್ 2Ag ಅಲ್ವಾ? ಅಟ್ ದಿ ಎಕ್ಸ್ಟ್ರೀಮ್ ಎಂಡ್ ಇದು ಆನೋಡು, ಇದು ಕ್ಯಾಥೋಡು, ಇದು ರೆಸ್ಪೆಕ್ಟಿವ್ ಅಯಾನ್ಸ್. Yes or no? Yeah, sorry guys. Actually this 2 is not necessary in your symbolic cell representation. ಈ 2 necessity ಇಲ್ಲ. ಇದು ರಿಯಾಕ್ಷನ್ ಬ್ಯಾಲೆನ್ಸ್ ಮಾಡೋದಕ್ಕೆ ಮಾತ್ರ 2 ಆ ತರ ನ್ಯೂಮರಿಕಲ್ ವ್ಯಾಲ್ಯೂಸ್ ಬರಬೇಕು. ಸಿಂಬಾಲಿಕಲ್ ಆಗಿ ಇಷ್ಟೇ ಇರಬೇಕು. Whatever the electrodes and the electrolytes are involved. Okay. So copper is undergoing as a Cu2 plus, Ag plus is taking as an Ag. No need of writing those 2 and all those numerical values over here. Just symbolical and what are the electrodes and what are the electrolytes, only that much has to be mentioned. Of course, here will be solid, here will be aqueous, here will be aqueous, and here will be solid. So in certain scenarios, our particular mention ಮಾಡಿರುತ್ತೆ that you are taking 1 molar or something 2 molar of electrolyte solution. So atara particular mention ಮಾಡಿದಾಗ aqueous ಬದಲು here you have to write in the bracket 1 molar. ಅವ್ರು ಏನ್ ಮೆನ್ಷನ್ ಮಾಡಿರುತ್ತೆ ಆ ಎಲೆಕ್ಟ್ರೋಲೈಟ್ ಇನ ಸೊಲ್ಯೂಷನ್ ಇನ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಆಗಿ ಮೆನ್ಷನ್ ಮಾಡಿದ್ರೆ ಬರ್ದ್ಬಿಡಿ. ಅಥವಾ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ಅಂತ ಅವರೇ ಹೇಳಿದಾಗ ನಿಮ್ಗೆ ಗೊತ್ತು ಇಟ್ ಇಸ್ ಅ ಯೂನಿಟಿ, ನೀವೇ ಬರೀಬಹುದು 1 molar ಅಂತ. Is that clear? I hope so. There is no doubt in it. Yes. Now for example, if you want to calculate the cell potential for this one, how will you calculate? E cell is equals to E right minus E left. That means E cathode minus E anode. Which is your cathode now? Yes. So E Ag plus bar Ag minus the standard electrode potential or the electrode potential of Cu2 plus bar Cu. So when you take the respective potential and take the difference of it, you will be getting the overall cell potential. So this is the way of representation of your galvanic cell and to calculate the cell potential of that particular cell. Is that clear? So these were the quite important things one has to know and one has to know to proceed further in this chapter. Okay. So in today's scenario and in today's video, we have come to know what do you mean by a half cell, how to write the oxidation half reaction and a reduction half reaction. We came to know what do you mean by a salt bridge. What are the importance of the salt bridge? We also came to know about electrode potential, standard electrode potential, and the most important thing we also came to know about cell potential and an important formula. First formula which is going to come in this electrochemistry, because there are many such formulas. The first formula you came to know about cell potential, which is about E right minus E left. That right and left, in order to understand that, you should know the concept of writing the galvanic cell symbolically. And we came to know about the symbolic representation of the galvanic cell, in which at the extreme ends you will be having the respective electrodes, which will be separated by its electrolytic solution by a single bar and by a salt bridge through a double bar. At the left you will be having a anode, and at the right you will be having your cathode. Then we also saw with certain examples, that is your Daniell cell, and also with a reaction. I can give you a task. Okay. You take the Daniell cells complete cell reaction. You take the Daniell cells complete cell reaction and try to write its galvanic cell symbolically. As we have dealt over here, ಇಲ್ಲಿ ಕೂಡ ರಿಯಾಕ್ಷನ್ ಬರ್ದಿ ನಾವು ಹೆಂಗೆ ತಗೊಂಡ್ವಿ, ಅಫ್ ಕೋರ್ಸ್ ಇಲ್ಲಿ ನಮಗೆ ಗೊತ್ತಿತ್ತು, ನಾ ಡೈರೆಕ್ಟ್ ಆಗಿ ಬರ್ದ್ಬಿಟ್ಟೆ Daniell cell ಗೆ. So now what I am giving you as a task is, you take directly the full cell reaction of the Daniell cell and you try to extract the galvanic cell symbolically. So you'll get a proper image. Because unless and until you don't try, you will not come to know. Is that clear? So these were some important facts one has to know before entering to the mainstream of this electrochemistry. So in our next video, we are going to see that how will you measure the electrode potential? How you are going to measure the electrode potential? Because when I was saying as a standard electrode potential, I have mentioned over there, according to IUPAC convention, always you have to take the reduction potential itself. Of course, there a question arises. ಅದು ಆಕ್ಸಿಡೇಷನ್ ಆಗ್ತಾ ಇದ್ರು ನಾವು ಹೆಂಗೆ ರಿಡಕ್ಷನ್ ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಕ್ಕಾಗುತ್ತೆ? So all those doubts will be cleared in my next video, where you will be understanding the concept of the measurement of your electrode potential. Very much important topic, okay? Because there will be understanding how a person will able to calculate the reduction potential, and he will be able to know that which electrode will be acting as a cathode and which electrode will be acting as an anode. Because ಇಲ್ಲಿವರೆಗೂ ನಾನಾಗೆ ಹೇಳ್ತಾ ಇದ್ದೆ, okay, this electrode was acting as an anode, this electrode was acting as a cathode. Of course, I'm not a god. Of course, I also need some practical evidences and a theoretical part. And those theoretical part will be dealt in my next video under the concept measurement of electrode potential. Till then, have a revision of all these topics we have learned so far, because the same topics applications will be seen in my later videos. Okay.